It's not very hard to figure these things out, okay?
Good.
Let's go. Okay. Yesterday, I started at the bottom when we talked about arc ignition, and it occurs by touch start or high frequency overlay. And those are really the only two mechanisms we have to start arcs very easily. And that means we need nice sharp chisel pointed tips on wires when we start them. We gotta end up getting rid of the drop that melts on the end of the electrode and oxidizes before we try to touch start again, and little things like that. So little details that you have to worry about if you're actually building robotic welding equipment. The next thing we talked about was these strong plasma jets, which are driven by the Lorentz forces, the J cross B forces, which actually creates a pumping action because I have a conical shaped arc, which gives me variable current density. Variable current density means the force is variable, and a variable force in a liquid means I'm driving that liquid, and I get velocities of 500 meters a second, or thereabouts. Those produce forces sufficient to depress the surface of the weld pool, particularly when we get above a couple hundred amps. And frankly, when you get to 1,000 amps, the plasma jets are usually so bad that you can't weld. You're just blowing metal all over everywhere rather than welding. Okay, so it's more like an arc gouging operation. You don't have to blow compressed air through there like arc gouging because the plasma jet does it for you, so far as that goes. So typically, that's why we don't weld above 400 or 500 amps in the open atmosphere. In submerged arc welding, we may go up to 600, 700, 800, or even 1,000 amps. But when we're doing 1,000 amps, first of all, it has to be very high productivity welding, such as making line pipe for Alaskan pipeline or something. You've got this 4-foot diameter, 3/4 inch thick steel pipe. So you're submerged arc welding the steel pipe. You basically start out with a plate like this table, turn it into a U shape in a great big press, and then you do an O-ing press, which takes the U shape and turns it into an O-shape pipe, and then you want to weld that seam. And you got miles and miles of this to do in a mill, and so they actually have multiple arcs. They have, well, they always use at least 2 arcs. Sometimes they use 3 arcs, 3 different power supplies spread over a distance of maybe 6 inches. And I've seen people doing research on trying to use 4 arcs. So you might be using the equivalent of 1,000 or 1,500 amps, but you're dividing it among multiple electrodes. Okay, so the plasma jets are still controlled. Or they also do fancy things where they're doing it AC and one arc is on while the other one's off. Okay, type of thing. So, I mean, this is all at 100 hertz or 60 hertz or something. It's called a Scott connection. Anyway, the plasma jets influence surface depression. We talked about yesterday. It influences drop transfer, which I didn't talk about yesterday. We talked about depressing the weld pool surface right here, and I said at about 150 amps you start to get a deep depression, which leads to defect formation, and I passed around one of these things that showed some defects. There's lots of different types of defects it can produce. And it also influences droplet transfer, because you'd like to have nice little uniform drops coming across this arc. And in fact, typically drops that are on the order of the diameter of the electrode tend to be some of the best drops. As you get to very high currents, you actually get smaller and smaller drops. Eventually you get into what we call streaming transfer, and you've got a continuous stream, very thin stream. But then there's some electromagnetic instabilities where that thing starts to form a helix. And if you go up in current, the helix starts throwing drops off to the side before they get to the pool. So
is that always in DC too, or is it?
That's in DC. You can get rid of some of that in AC, but there's other problems with AC in terms of quality, because with AC you're kind of interrupting some of this fluid flow, and you can get air into the arc and other stuff.
What force is causing the helix then? I know we talked about yesterday.
It's electromagnetic in the sense that if everything was perfectly aligned axially, there would be no force. But if there's any misalignment from off-center, then now there's an electromagnetic force. If you do the J cross B with that permutation, you now get a circumferential force. Remember, if the J cross B is all purely axial and circumferential, you get a radially directed inward force. But now if I'm off to the side a little bit, that gives me a component in the radial direction, which is going to give me a circumferential force,
Okay.
a component of current in the radial direction, which is going to give me that crossed with the circular magnetic field is going to give me a force circumferentially, and that's what creates the helix.
Okay.
Okay, and in fact, that's what I may remember when I talked about fluorescent lights. I said the electrons actually travel in a helical path. That's the reason. Okay, there is this J cross B force on the electrons. So in any case, you like the drops to be small, but not too small. When I get to some cases, I can actually have not only a plasma jet coming from the tip of this electrode up here, I actually can have anode spots form where the current tends to concentrate for various reasons that we don't fully understand. I'm sorry, this is the cathode down here. This is the anode if this is gas metal arc welding. So this is a cathode spot. And the cathode spot, the current comes out at a much higher current density, and you actually can get jets shooting up from the surface, which are trying to blow the drops off to the side. And so if you go to very high current, this occurs typically in CO2 or helium welding for reasons that aren't completely understood, although I have some theories that has to do with heat transfer right in this boundary layer down here with the higher conductivity gases, remember, but I've never proved that. I never found someone who wanted to fund it. But in any case, so it influences drop transfer. We talked about surface depression and defect formation. We didn't talk about arc stiffness, but clearly, if I have this jet, the stronger the jet gets, the stiffer the arc. And in fact, in a welding power supply, again, something that you don't really see usually, although some welding power supplies will have a knob on there and it will say arc stiffness, and you can turn it up or down, because if you're welding outdoors and the wind is blowing by, you want to have a stiff arc so the wind doesn't blow your arc out, okay, or blow it away so that you're not welding so that the arc is going off the joint. You miss the joint because of the wind blowing. Significant problem outdoors. I think I told you I went on top of the Boston Convention Center a few weeks ago where they were welding some stainless steel roof decking, and there's like 40-mile-an-hour winds. In general, you cannot weld above about 10-mile-an-hour wind. You got to have some shielding, and they tried to build some little tents, and the tents weren't good enough, and they were getting some lousy-looking welds because the arc was being blown away, the shielding gas is being blown away. But anyway, you'll see a knob for arc stiffness, and the welder doesn't see, they might hear something in the arc, but if you go to higher average current, the stiffness is going to be proportional to the current squared. And so what you do, if I had a current versus time that was 100 amps or 150 or 200 amps, absolutely flat DC, you would not really hear that arc. But if you've ever listened to a welding arc, it kind of crackles. Sometimes people describe it as bacon cooking, okay, a little crackling. And that's because if you just take a three-phase transformer rectifier power supply, you'll have 30% ripple on that. When you rectify that, you end up with 30% ripple. You don't have a pure DC current, you've got a ripple on here. And if you square the higher current, well, this is the maximum current versus the average current squared, or you want to take the ratio of this and the minor, because it's a squared, it's not a linear average, you actually get a higher effective plasma jet, or a stronger plasma jet, because squaring of the peak current here is greater than squaring the average of the max and minimum. Okay? So if you took 1/2 I squared max and 1/2 I plus 1/2 I squared minimum, it would be larger than the average current squared. And so you actually can get a stiffer arc. And so if you have a knob on your power supply, all it does a poorer job of rectifying it. Okay, you're taking out some of the inductance in the system that tends to smooth out the rectification if you're an electrical engineer. So anyway, you can get a stiffer arc. And nowadays, we have inverter power supplies, which an inverter power supply, the old transformer rectifier power supplies from the the 50s and 60s weighed 1,000 pounds. You'd have a 300-pound inductor and a 400-pound transformer in there to control this 500 or 600 amps in your power supply. And so there's a huge amount of copper in there and fairly expensive, and you have to have cranes carry it around if you want to move it. And starting in the early 80s, as they got better and better semiconductors that could handle 500 or 600 amps. The early semiconductors, back when I was a student, I actually had a transistor that would handle 1,000 amps. But I paid $5,000 for that one transistor, and it was the size of this, okay? And it was actually a bunch of transistors inside, but in a triple Darlington connection if you're an electrical engineer. But as they got silicon-controlled rectifiers that can control 100 or 200 amps, and eventually we got to the point where we have not just SCRs, but what we call inverters that can control not only 200 or 300 amps, but even 500 or 600 amps. You actually, with semiconductor technology, you take your incoming AC, you convert it to DC, you then chop it with the semiconductor to 20 kilohertz or 40 kilohertz. So you got very high frequency AC, and now you transform that to the voltage that you want, because you can use very small iron cores when you go to higher frequency. If any of you ever worked on aircraft, they don't use 60 hertz, they use 400 hertz. Anybody know why? It's because they're weight critical, and if you're at 400 hertz, you need smaller magnetic cores in all your transformers. Even if it's a little fan motor, it can be much smaller. I think it goes as the square of the frequency, if I remember. So the weight of your, if you go from 60 to 400, you have a tremendous weight reduction in all the iron you have to have in all your transformers on that aircraft. So they use 400 hertz. Now, I don't know, does any of the Navy ships use?
A lot of combat system stuff.
But it's
Part of
partly
it's for noise, part of it's for
okay.
weight though too, with spy.
Okay, if it's for noise, that may be true, but a lot of it's for weight, and it may be because that 400 hertz system is available because of the aircraft industry. Okay, I mean, you don't want to build that whole infrastructure of making all these little motors and transformers unless they already exist for something else. So you can save weight, and it's already available, but you save weight. Well, because of the inverter technology, you now can get a 60-pound welding power supply that a guy can carry from place to place. He can plug in, and it'll control 200 or 300 amps, and it'll give clean. It can give very clean DC, like this solid line here, if you wanted, but you don't really want that. But what it can give you is well, let's draw it lower. I'll draw it on top of this. It can give you a low current with very high frequency spikes and very high pulses. So you might have a 200 amp average, but you could have a 100 amp base and a 300 amp peak. And if you do this at 100 or 200 hertz, you can get what we call 1 drop per pulse. And that is just like milking the cow again. Okay? If I do this at the droplet transfer frequency, which is on the order of 100 to 200 hertz, I can squeeze off 1 drop at a time. And this is great for welding sheet metal. In fact, that's one of the things that I recommended they do up there. It also gives you a much stiffer arc for the same averaging reasons we talked about before. And I suggested they were doing gas metal arc welding up there. Or no, they were doing TIG welding. That's one of the problems why it's going to be so slow. And I suggested they think about going to gas metal arc. If you try to do regular gas metal arc with the old transformer rectifier type things on 16th inch thick steel, you either use globular transfer, which is relatively low current density, where you're just kind of dropping turds on the plate, okay? And it creates all kinds of lack of fusion defects. If you try to go in there with what we call spray transfer, where the drops are on the order of the electrode, you'll just burn right through there. The guy can't control it. Certainly a manual welder can't control the pool on a very thin plate. Okay, so it gives us a lot of capability. It also allows a welder not to have to call the cranesman in when he wants to move where he's doing his welding. Okay. So that's an inverter power supplies. And that's probably enough on plasma jets. Let me see if there's anything else. It also can influence metal vapor in the arc, fume formation. In fact, back in the early 90s, John Deere Corporation each August will have a kind of a couple of hundred of their welding engineers and welding technicians come into Dubuque or Des Moines, I can't remember. It must have been Dubuque, Iowa. And they have a little 3-day welding seminar for them in the middle of August because there's no real work going on. Everybody else is on vacation. And so they used to ask me to come out and give a lecture. And so one time in the early 90s, I was out there and I was talking about gas metal arc welding, which is what they use in most of their plants to make their tractors. At the time, OSHA was talking about reducing the total level of fume that the welders breathe. It used to be 5 milligrams per cubic meter. Cubic centimeter? 5 milligrams per cubic meter, I guess. That makes more sense. Anyway, they knew they were going to have some problems in some parts of their plant where there's kind of smoky. And they were going to have to spend millions and millions of dollars in their plants to get fume extraction equipment so they could meet these new requirements. And I was talking about some of the gas metal arc transfer and things that I don't really include much in this course anymore, but I was talking about it and the guy came up to me and says, was there any way we can reduce the heat at the tip of that electrode? Okay. And see, remember, the current is what carries the heat, and the vaporization, if I try to carry more current in there, the heat is just, a lot of it is not going to go into more efficient melting because I can't force heat to diffuse through the liquid and the solid any faster. The excess heat will just form more fume. And so he says, is there anything we can do to reduce fume formation? I said, well, the pulse current welders, this is 15 years ago, were getting more practical from an economic standpoint. They started in the 80s, but they were like $40,000 units. But by the early 90s, there were $5,000 units. Now you can get them for $2,000 or $3,000. Okay, but so they're getting down. So that's what people use now, just because they're lightweight and stuff. Anyway, I said you could use an inverter power supply and use pulse current welding, and probably get the same amount of average heat transfer. I just erased it, but I could get the same average, which goes linearly, but the fume formation is going to go as the square of the current. And I could get, fume formation rate will go as the current average linear, but the stiffness and drop formation can go as the square. And I said, so you can try pulse current welding. Well, he went out and tried it and found a 60% reduction in fume. And so all of a sudden I was a hero in the industry. And again, just sort of dumb luck. He asked the question, and I kind of went back to the basics. And I was just guessing, I didn't know, just trying to be helpful. But it works. You can reduce fume formation by pulse current welding. Okay. So enough for surface depression and plasma jets and things like that. I could actually spend another hour on plasma jets. This is kind of one of my pet areas. But let's go to heat flow. Anybody have any questions before we get to heat flow? Okay. You have a handout, so just so you have something in my personal hand, right? Handwritten notes on heat flow during welding, okay? This is something you don't need to know, but you can go back for a non-traveling heat source, and you can go look in textbooks. I could have brought it. Karslow and Jaeger is this textbook on heat flow and welding, not heat flow and welding, heat conduction in solids. So mathematical text, and it's just solutions to the diffusion equation for diffusion of heat in solids. And you can go in there and look up the one-dimensional planar solution. So if I have two bars and a heat source, a theoretical heat source is just a planar heat source on that surface, you can look at how the heat diffuses away into the solid material on either side, and the temperature minus the reference ambient temperature is the heat divided by the area, the intensity of the heat source divided by the area, 4 pi alpha, which is the thermal diffusivity, which is K over race, well, actually I'll write that down. Alpha, which we mentioned before, is equal to the thermal conductivity divided by the density times the heat capacity. Okay, that's a rho. And all you're solving is Fick's second law of heat conduction, which just says something like dt, temperature with respect to time, equals alpha d squared x, or d squared, what's d squared up? Alpha d, yeah, d squared t dx squared. D squared x, okay. Or something like that. Okay, this is just grad squared, right? We talked about yesterday, L squared. So this is the thermal transient of heat. It's also the diffusion equation. It's the same for mass diffusion, it's the same for momentum diffusion and fluid flow. You can take the whole thing as the diffusion equation. Anyway, if you solve it, if you solve that differential equation for these boundary conditions of a planar heat source, kind of a one-dimensional heat flow linearly, you'll get 4 squared alpha t quantity to 1/2, 1 over rho c to p exponential of minus x squared over 4 alpha t. Now, exponential of minus x squared, what's that? Anybody know what the name of that shape of that curve is? It has a particular name. It's called the Gaussian distribution. Ever heard of the Gaussian distribution? Flip coins. Go over here to the Museum of Science and they have little balls dropping into slots, and it shows over time these 300 balls or whatever will form a Gaussian distribution every time you run the experiment over there, which is about 5 times an hour. Okay. What you get a Gaussian distribution that looks like this. At a longer time, T2, you get another Gaussian, but the mountain looks like the Appalachians rather than the Rocky Mountains. Okay, it still has a Gaussian shape, but a Gaussian is just exponential of minus x squared. So you get a Gaussian, the heat's just diffusing away, kind of like flipping a coin. We call it a random walk in mathematics. Okay, you can think of little billiard balls, atoms, bouncing around carrying heat, and sometimes there's a probability that they will go to the right, and there's an equal probability they'll go to the left. That's why it's like flipping coins. But if you look at that and they all start at a line in the center, if you look at it some later time, some of them will diffuse left, some of them will diffuse right, and the average shape will be a Gaussian. Okay? It's just statistics, so far as that goes. So what is this like? Well, this is sort of like a friction flow, right? So this would be solution. It's not a traveling heat source. All your heat's generated at a plane, and the heat's diffusing away. So this is the solution to the temperature field of a Gaussian. Now you go to a 2-dimensional heat source, where you have a line. That was 1-dimensional heat flow. This is heat flow in 2 dimensions. So I've got a line source through the thickness of the plate. So if I had a hot wire in the middle of something and electrically heat it, the heat would diffuse out, but now I form a 2-dimensional Gaussian. So this really is a mountain shape in 3 dimensions. Whereas the other one was just a mountain shape in 2 dimensions. This is a hump. Okay, I'm trying to draw this as a mountain here. And this would be the same thing, only in this case it's Q over delta. The other one was, this is intensity over a distance, over a length line, whereas the other one was over an area. Okay, and now this becomes 2 halves rather than 1/2, but this is now minus r squared, where r is just the square root of x squared plus y squared. But this is also a Gaussian, but it's a Gaussian with respect to the radius from this line source rather than distance x. So basically it's just kind of moving along. This is equivalent to deep penetration laser electron beam. Line source move, it moves through the solid, although it's not moving yet. And so you go to Karslow and Jaeger, and you look at the solution for a 3-dimensional heat flow from a point source embedded on the inside of a surface, and you'll find that if you look at it radially, this is a buried point heat source with heat going out uniformly. You can think of spherical waves going out into space or something, right? The shape of the Earth, spherical waves coming from this point. Isotherms are spheres around this until they hit the surface. You'll get a bunch of Gaussian shape if you temperature versus radius, and I can't draw spheres like this, but you'll see it like this, okay? Now, that's three-dimensional, and this is sort of like arc welding if I split the whole thing in two, and so you can do a stationary arc on the surface of a plate by just dividing cube by 2. Because this is a solution for a full cube, half of it going up and half of it going down. If I want to look at a cube, such a heating of an infinite plate on the top surface, by symmetry I can eliminate the top, and just all I have to do is divide that by 2, the cube by 2, and I'll end up with my temperature field. Now a guy named Rosenthal, and Daniel Rosenthal, sort of an interesting guy. He was Jewish in the 1930s. He was, I think, in the Netherlands, and initially he was fleeing Hitler in the late 30s, and he went to Mexico or South America. Anyway, went somewhere, just had to get out of Europe. And then by 1940, he was over here in building 2, or building, no, he was in building, what building are you guys in? You're not, are you at 5? Okay, what's the one closer? 3? Was it 3? So I think he was over here at building 3. Anyway, he's in mechanical engineering at MIT. And in like 1941, he published the Rosenthal moving point source solution, where he basically took this this three-dimensional Gaussian point source, and he made it move with a certain velocity. And he ends up with an equation that looks like this, where there's your Q, 2 pi, it turns out it's K, get rid of the alpha here. Anyway, it's 1 over r, the radius. This is the velocity of moving, and this v over 2 alpha times r, or x, v times the distance divided by 2 alpha is a dimensionless number called the Peclet number. And it has to do with moving sources of heat or whatever. Moving in the x direction at velocity v, q is the strength of the heat source, and for the next 30 years, this was the solution in welding to heat flow equations, because we didn't have fancy computers until the 80s that could really solve these problems.
How realistic is the three-dimensional example for arc welding? Because doesn't it assume it's uniform?
I'll get there. Okay. It assumes everything is a point source, and it's not really a point source. As you get closer to the source, the solution becomes less accurate. So the next big thing was in 1965, and Niels Christensen, a professor at Trondheim University in Norway, broke his leg or something. Anyway, he was laid up for a year in bed. And so he took Rosenthal's solution and he put it into dimensionless form, which looks like this. Okay, just took that equation, made it dimensionless, so you get a bunch of dimensionless plots. Now, why is Niels Christensen important? Well, I already told you that Daniel Rosenthal published his work. He actually was probably doing it as he was going across the ocean over here to North America and doing the work. He finally got here, but when he published it, it says, if you read the original paper, 1941, it says he was at the Mechanical Engineering Department at MIT. Niels Christensen has a World War II MIT connection in that during World War II, he was actually a, I don't know if you call him freedom fighter, but he was basically skiing across from Sweden into Norway fighting the Nazis. Okay, Sweden was neutral, and Niels was kind of fighting for the Allies and fighting the Nazis in Germany by skiing over the mountains and shooting up Nazis and skiing back. After the war, he got a fellowship. I don't know if it was, can't remember what kind of fellowship it was, but he did his doctoral thesis right over here in Building 8, in the basement, with John Chipman. Okay, John Chipman was the department head back in the late 40s, and he did his thesis on welding flux. John Chipman had kind of learned how to deal with steel fluxes and melting of steel, and Niels Christensen wanted to study welding after World War II, so he came over here and studied welding fluxes. And I think it's Welding Research Council bulletin like number 10. There's about 300 or 400 of them now. But it was publication of part of his doctoral thesis work. But it turns out he had to do his doctoral thesis work twice, because back then you didn't store all your data on a computer. You had a laboratory notebook. And as he had finished all his work and knew his results and was starting to write his thesis, someone stole his laboratory notebook. And they actually thought is it was actually communist spies who were roaming the halls of MIT looking for data. But Christensen's notebook with all the data was stolen, so he had to stay another year and repeat all his experiments. But fortunately, that company knew which ones to do and how to do them. So it only took about a year to finish it. But Niels Christensen went back, became a professor over at Trondheim, and he ended up doing the next big step in Rosenthal solution by putting everything in the 60s in dimensionless form. So you had dimensionless graphs. If you know how to read the dimensionless graphs, you could now look at the heat flow of a traveling point heat source. But as Brian pointed out, the problem with that is as you get closer and closer to the point heat source, it becomes more and more unrealistic because the heat source to the surface from this arc is actually sort of a Gaussian. The current distribution is not a point source of current that comes right here that would give you a perfectly semicircular shaped well pool, which is what comes out of these solutions. It's really a Gaussian solution. And so in 1978, here at MIT again, the next big thing was it 78? No, it couldn't have been 78. It was 84, 85. So we go from 1948 was Rosenthal to 1964, or actually I think it's 66. And I gave you a copy of Christensen in your notes. There's a copy of Christensen's paper in the British Welding Journal where he puts it in dimensionless form. But in 1984, a student of mine, Nunsen Chai, basically took, if you have a point source solution, have you learned about Green's functions yet? You learned about Green's function? He did a Green's function solution, so he could come up with any distribution you want, but he actually did the Gaussian solution. So you put in, and then he measured what the Gaussian distribution of heat was on an arc, and he put that solution in. And so now, rather than perfectly semicircular shaped well pools, you can get more realistically shaped well pools for flat surfaces. At the time, he was using a PEP-23 computer, and he would run it over the weekend to solve this thing. Today, it'd probably take 2 seconds on one of your laptops. Okay, but anyway, I always thought it was interesting that those heat flow solutions all came out of MIT about 20 years, or 15, 20 years apart. So those are the solutions, for whatever it's worth. You have the handout. And actually going back to Christensen's paper, these are actually plots out of Niels Christensen's paper of some of the dimensionless parameters. This is figure 15 from his paper, approximate distribution of temperatures. So anyway, and Brian, as you get closer, you can now approximate it by Green's function, and you get more realistic values as you get closer to the well pool. But this is the type of three-dimensional temperature distribution you have from an arc weld on a surface. And if you want to look at, there's plenty of other pictures that he's got in his paper. Here are just slices through that three-dimensional surface, dimensionless surface, and this theta over n, which n is what he called the operating parameter, and this is different values, but you can see the spike of current. Now, one of the problems with the point heat source solution, mathematics doesn't like point sources, and so the temperature goes to infinity at the origin. Okay, when you have this kind of sharp spike, temperature goes to infinity, which is not realistic. But you can see the Gaussian shapes if you look at the going off to the side. This is still diffusing to the side as a Gaussian, but in the other direction, where it's traveling along, I get a distorted Gaussian. Okay, because I'm pushing my Gaussian on one side and tailing it off to the other end. And if I look down from the top, these are my isotherms, and one of these would correspond to the shape of the elliptical weld pool. And Christensen has some experiments and stuff in his paper verifying distances and lengths and shapes of the weld pools that you would expect. Now, if you vary the operating parameter, this is theta over n. If you're stationary, everything's a bunch of circles in terms of the isotherms, okay, the constant temperatures coming out from here. If you go a little faster, you start to get these sort of somewhat elliptical shaped things, but near the origin it still looks like a circle. As you get further away, it gets more elliptical. You go even faster, and you get these big ellipses, and you actually can plot across here where the the temperature where this the tangent to the isotherm is horizontal, you can plot that locus of points as this dashed line, and that is your locus of maximum temperatures, and you can figure out what the width of your heat effective zone should be from all of this. This is something going very fast, like a laser and electron beam, and now your locus of temperatures looks like this, and you actually find that things are reaching their maximum temperature. If this is the size of the well pool, the maximum temperature is reached well after the heat source is passed, because the heat's diffusing from the liquid into the solid, and it takes time to do that. And this is where I say the heat effective zone in laser and electron beam is controlled on cooling, where this is the locus here for a slow arc weld, and the maximum heat effective zone is actually controlled during heating. While that pool is coming along, you get to the maximum heat effective zone while the heat source is still present at that point. Okay?
So what would it look like for a friction stir where you're not actually melting? Because they have a thermomechanically recrystallized zone.
Well, you don't have to melt. The problem is you really ought to go to an unsenchized solution, because you now have a heat source that's big compared to what you're doing in the process you're doing. It probably would look something like this. Okay, it's not, friction stir is not the fastest process, but it would look something like this one. Okay, as far as that goes. But you really ought to be doing the Green's function solution as far as that goes. Okay, so that's, you can get very sophisticated nowadays with powerful computers, and you're basically going to solve several types of equations, and people have been publishing papers for the last 20 years on non-Gaussian temperature distributions, because it can be done in the computer. Okay? However, what we've really learned is that it's not just that, it's what happens afterwards. Even though you have the same temperature distribution on the surface, it depends on whether you have convection that pulls the heat from the top surface and pulls it down to dig a hole, or whether, in certain cases, you have the same type of Gaussian distribution on the top surface, but you'll get a broad, shallow penetration because the fluid flow is going that way, and the hot surface right underneath here, the heat's being carried out and widening the well pool and not getting very good depth. And it turns out, I actually should have a sample here on some titanium. See if you can see it anymore. Let's see if I go on that. What do I have here? Oh, this is, that's titanium too. Well, these need to be re-etched. They're about 20 years old. But in any case, I mean, if people want to come look at it, but we really ought to re-etch them. You can't see them very well anymore. By putting fluxes on the surface, well, let me back up. We learned, well, let me back up even further. Back when I was working as a welding engineer at Bethlehem Steel, a guy at Westinghouse Bettis was very concerned about this because they were actually welding zircaloy tubing. And they found they could get a difference in penetration on gas tungsten arc welding of about a factor of 3, depending on what composition of zircaloy they were welding with. And it turns out it depended on how much chloride was in there. And even though people on the videotape didn't hear what we talked about just before class started, zircaloy, zirconium alloys are refined out of zirconium tetrachloride, and some of the zircaloy alloys had a lot of chlorine. And with a lot of chlorine, they got shallow penetration. With little chlorine, and we're talking parts per million, like 100 parts per million here, of chlorine in the alloy, they could get, with little zirconium or chlorine, they could get deep penetration. And it was a factor of 3. And when you're trying to run an automatic process on nuclear material, you can screw up everything by having this kind of variation in penetration. And at the time, in the mid-70s, this guy at Westinghouse Bettis wrote a review article on this, and he went back and showed not only did it occur in zircaloy, it occurred in a bunch of other alloys systems. with different things. Minor impurities in the order of parts per million were causing tremendous differences in the penetration. Within about 2 or 3 years, a guy named Scott Mills out at Rocky Flats, where they build nuclear weapons, came up with a theory that it was convection in the well pool that was doing this. People had all kinds of theories before this. And Scott Mills did some experiments and showed that it was surface tension driven flows, which we call Marangoni flows after an Italian physicist in the 19th century. Okay? But you can have surface tension driven flows. Basically, the little bit of chlorine was causing a chemical gradient. So if the temperature derivative of surface tension was negative, you would get flow like this. And if the temperature derivative of surface tension was greater than 0, whoops, have I got this backwards? I got it backwards. This one's greater than 0, this one's less than 0. You would get flow like this. And it's because the liquid is trying to minimize the surface tension across the whole surface. If I have highest temperatures here, and I can bring in lower surface energy material from the sides, this is the type of convection I will get. And it turns out, if you just look at buoyant, we did a paper in 1983, which I think I've given you a copy of, that we did the calculations in the computer and showed that for pure buoyancy, you'd have velocities on the order of 1/10 of a meter per second in the well pool. For pure electromagnetic flows, you would have about 1 meter per second. And for Marangoni or surface tension, you have something like 10 meters per second flow in the well pool. So it goes up by an order of magnitude with each one. Okay? So electromagnetic usually controls, but if you have certain amounts of impurities, small amounts of impurities. So by 1980, it turns out this was the biggest problem in the stainless steel industry. It turns out that, in fact, my first big consulting job, the one that I bought my first new car on, had to do with a problem in a brewery in upstate New York. And they had welded the stainless steel beer kegs. And one company had welded 400,000 of them, and they knew about this problem. Every coil of steel that came in from the stainless steel company, they would run a welding test to find out whether it penetrated deep or shallow. And they would segregate their coils of steel and change the robotic welding process to account for the variation. They just changed the current depending on the coil of steel. They made 400,000 with very few defects. Another company was making 75,000, didn't know about the problem, just threw all the coils in there together, tried to run it, and I estimated that 80% of their kegs were junk as defects. Ultimately, they had to do a $10 million repair on $7 million worth of product, okay, which is another story we don't have time for. But it was, 25 years ago, this was the biggest problem in the steel industry because people didn't know how to control this, okay? You could, if you measured it for each coil of steel, but that's extra work and everything else. So fairly small differences. So the shape of your heat source is important, but convection in the well pool is even more important in controlling what actually goes on. And as you get to higher currents, it turns out surface depression is even more important, okay, in controlling the depth of penetration. So it basically gets to be fairly complex as you get into things in greater and greater detail. Now I didn't finish heat flow, but actually why don't I take, we started a little bit late, so why don't I take a couple minutes and talk about, rather than just this other heat flow, let's talk about how convergent and divergent heat flow. Okay. Now, so there's all these fancy equations, and I told you I'm not going to try to turn this into a math course. So now I'm going to tell you how to solve all the heat flow equations in your head, 95% of the time, with good accuracy. This also allows you to solve about 30 to 40% of your homework problems. Okay. because it actually is an equation I can make you solve the equation. You know, that's how homework problems work, right? Well, it turns out every one of those solutions, whether it's point, line, or area solution, planar heat flow source, has this dimensionless number, x over the square root of alpha t. Alpha is the thermal diffusivity. It has units of centimeters squared per second. So if I've got centimeters squared per second times seconds, that's centimeters squared. I think the square root of it is centimeters. X is centimeters, so the whole thing's dimensionless. This is known, what is this known as? Fourier number. Okay, there you go. Fourier's, well, we're not doing, for heat flow rather than, actually I said that was fixed second law. That's Fourier's second law. Fixed is for mass diffusion. Sorry. Fourier's second law of heat conduction. Fixed second law just looks like, instead of temperature, we're talking about concentration of mass, atoms. But Fourier's second law has this alpha in it. It's fundamental to the equation, and every solution, whether it's the Gaussian, which is just x squared over alpha t for the Gaussian, or it's an error function, or it's a Bessel function, you get all kinds of fancy solutions out of Carr's law and Jaeger, but every one of them has this dimensionless number. You can't take the exponential of something that has units. It has to be a pure number, meaning it has no units. So this is the pure number, the dimensionless number, which is the Fourier number. And with the Fourier number, you can very quickly determine if the Fourier number is 1 and the thickness of your material is x. With the Fourier number of 1, if you put a heat source on one surface and let the heat diffuse in, it will decay. It's not a 45-degree slope, but it kind of decays from the maximum temperature down towards the ambient temperature within 10% of it over the thickness of your sample. If your sample is very thick, which could be the same sample just at much shorter times, okay, that means the Fourier number is 10, because x is 10 times larger than the square root of alpha t. The heat just barely diffuses in to 10% of its value, and most of the sample is not even heated. If the Fourier number is very low, the heat diffuses in, it runs up against the back surface of the solid, and it starts to accumulate here, and it never gets down, the sample never gets down until when 10% of the ambient temperature. It heated up. So this is the thick solution, the thin solution, and here when the two are nearly equal, you end up with a solution that you actually are going to have to solve in the computer. For all other cases, you either find that you're not saturated with heat, or you are saturated with heat. So 95% of the time, you're going to find that you're either thick or thin, and you can estimate whether there's any reasonable gradient across there. In the thin solution, there's no gradient across the sample of heat. In the thick solution, there's a huge gradient. Okay? And all you need to do is figure out how far from this simple little formula is x over alpha square root of alpha t equal to 1, or is it greater than 1, or is it less than 1? Most of the time, it's much greater or much less. It's 3 or a third or something. And if it's more than a factor of 3 from 1, then you basically can say the sample is either saturated or not saturated. You can also look at this and say, well, there's some finer points. Is the heat converging? If I'm heating a rod or a sphere, is the heat converging from a large diameter to a smaller diameter? Or is it divergent? It's going outward from a small diameter to a larger diameter. And you can kind of draw these things and say, well, if it's divergent, it's like a thick solution, and if it's convergent, it's saturating it more readily with heat. So you get some feel, you have to kind of get some feel, but we can use this to come up with estimates. The Fourier number is FO, is what people use. That's the Fourier number, and you're solving the second Fourier's second law, and typical values of alpha, and I gave you a handout of something I wrote in the Welding handbook that gives you a table of a lot more alphas. But copper is about 1 centimeter squared per second. Iron is 1/10 of that. Aluminum somewhere in between. Stainless steel is about half of iron, and titanium is about half of iron. And I think I mentioned that plutonium is about 0.02. But basically, all metals kind of fall in this fairly narrow range between 0.02 and 1 from very high thermal conductivity. Now, the highest thermal conductivity is gold, which is about alpha 1.2. And silver is about alpha 1.1. Okay? But basically, copper is like number 3 on the periodic table. Most things are down here in the iron range. Iron's sort of typical of most metals. Yeah.
What about lead?
Lead, I'd have to look it up in the table, but I think lead is like 0.3 or something.
Really?
It's, I mean, it's got a high density. I'd have to look up lead. It's not, as I remember, lead is actually a reasonably good thermal conductor. Not aluminum, but not as bad as iron. That's what I remember, but I gotta look it up. Okay. But it's sort of amazing. It's only the highly alloyed things, like stainless steel and some titanium alloys, that are really low. Okay, that has to do with things we don't have to get in, photons and things like that, as far as that goes. The thermal conductivity is related also to the electrical conductivity. We don't have to get into that right now. But to take a typical solution of something, if I want to know the heat, estimate the width of a heat effector zone in an arc weld, X is going to be proportional square root of alpha T. The interaction time is the length of the weld pool. That's how long the heat source is heating up the material in the heat effector zone just next to it, divided by the travel velocity. So a length divided by a velocity is equal to a time. That's the interaction time. If this is steel, alpha is 0.1 centimeters squared per second. If the size of the weld pool is about 3/8 of an inch or a centimeter, and I'm going at a typical travel speed for an arc weld of 0.5 centimeter squared per second, I end up with X is 4 millimeters. I look at an arc weld, and this heat effector zone width is on the order of 4 millimeters, within a factor of 1.5 or 2. Now, that's a lot easier than solving the differential equation. Okay? And remember, yesterday I was talking about this stud weld, and I said, gee, we had a 1/2-inch plate or something like this, and we put 2,000 amps in, or we might, oh, I said we had an 1/8 of an inch plate on bridge decking, and I said, you got this 1/8 of an inch plate, and you got a 1/2-inch stud, and you weld the whole thing in about 1/3 of a second, okay? And it's steel, and why in 1/3 of a second do I not melt through with 800 amps this lousy little 1/8-inch plate? Well, I can figure it out. How far does the heat travel in 1/3 of a second into steel? Square root of 0.1 times 0.3 seconds is 0.03 square root, which, what's that? It's like 0.2 centimeters, right? 0.2 times 0.2 is 0.04. Okay, did I get that right? So we're just going to say it's 0.2 centimeters or 2 millimeters. 1/8 of an inch is 3 millimeters. I drop to 1/10, 10% of my value of the heat in 2 millimeters. The back of this is still cold when the arc is done. That's why I didn't blow through. See how I can use that? And I didn't have to solve the differential equation. Yes?
When we were talking about that, are those bolts there to hold the rebar up in the concrete?
No.
What
They're there to attach the concrete when it solidifies to the decking. You don't want the decking to delaminate from the concrete. So you already got rebar up there, and the rebar gives strength to that concrete deck when you pour it on there, but you want to attach that whole thing to the steel decking that's holding underneath it.
So really, once this is all said and done, that is to hold the steel decking onto the concrete, not vice versa.
Right, right.
Okay.
And that's why it's got a little hat, bolt hat type of shape here, because the concrete casts underneath it, and you have to break the concrete to pull it apart. Okay? So there's another solution here. Time to penetrate 12 inches of steel. X is for 12 inches is about 30 centimeters. And if I want to know the time in this case, 30 centimeters squared is 900 divided by a tenth, 9,000 seconds to penetrate 12 inches of steel is 2.5 hours. And so I can tell you a story, actually it's in one of the fracture things, about the failure of the tail shaft on the LNG Libra, which was a liquid natural gas tanker that stopped dead in the middle of the Philippine Sea because of a fracture. I think I mentioned this to you. It had a football-sized defect in the center of it, which grew by fatigue and service until the 33-inch diameter tail shaft fractured. Well, a 33-inch diameter tail shaft it's convergent heat flow, so the radius is 16 inches, but it's convergent heat flow, so it's sort of equivalent to trying to diffuse heat in 12 inches. It would take 2.5 hours in the furnace to get the center up to 10% of the ambient value. And that ended up creating significant residual stresses when they put it in the furnace that caused the defect that we can talk about another time. Okay, enough for today. We can talk about tomorrow.